Hello everyone, I'm Siddharthan. Currently, we are in the second module of our deep learning course where we are discussing about mathematics for deep learning. And in this math section, currently we are in the statistics topics. And in today's video, let's discuss about measure of spread that comprises of the measures such as range, variance, and standard deviation. So first, let's try to understand about this measure of spread, what it is all about, and then try to understand about each of these individual topics such as range, variance, and standard deviation in detail with some calculation, and also how these metrics are useful in the case of deep learning. So this will be the agenda for today's video, and let's get started. So first let's try to understand about this measure of spread. So the previous topic was about the measure of central tendencies where we want to represent a data by a single value such as a mean of a data set, median of a data set. And this measure of spread is kind of different from what we have discussed there. And this measure of spread is all about describing how much data values differ from each other's, helping us understand the variability or dispersion within a data set. Okay, so as the name suggests, we are kind of trying to focus on the spread or how each values in a data set are different from each other. Let's say that you have 10 values in a data set, 10 data points in a data set, and how each of these values differ from each other's. And that difference we are quantifying using this measure of spread. And this, as I said, helps to understand the variability or dispersion within a data set. Dispersion in the sense like how the values are dispersed, what's the range or the numbers in which the values are dispersed. So that's about this measure of spread. So let's say that there are three friends, and each of these friends has a jar that has like candies in them. So one friend has 10 candies, the other friend has 5 candies, and the other friend has like 15 candies, and so on. So this is our small data set comprising of 3 people and the jars that they have. And measure of spread tells us how the values are distributed between these 3 friends, right? So between those 10, 5, and 15 values, so how the data is spread. So that's like the simple explanation for that. So once you are clear with the definition, we can move to the next part, that is like what's the importance of this. So specific to deep learning, the measure of spread values such as this range, standard deviation, variance, so these helps in understanding the data spread. And this data spread is going to helps in it's going to help us in the model performance. So some of this metrics gives us an idea of how the model is performing on the training data set as well as the real data set. And also range and other factors are useful in the outlier detection. So the values that are lying in the extreme ranges, we can call them as outliers. So it's helpful in that part. And also setting the model parameters. So how you're going to set your parameters. So we have this concept of gradient descent, right? Gradient descent, and it kind of plays a role as well. So we can see like the variance of gradients, and that tells us like how the values are getting updated and so on. So it's okay if you don't understand these applications. So we will discuss that in detail in this upcoming slides. But for now, you can just understand that these are some of the areas where this measure of spread values are kind of like helpful to us. And there are 3 main measures for this measure of spread, and these includes range, and then we have a variance, and then we have standard deviation. So in the upcoming slides, let's understand about these each of these things in a simple way, and also like what's the definition, formulas, and how to calculate this given a sample data set. And finally again, we will discuss about these you know applications of these metrics in detail in the context of deep learning. So first, let's just take a simple example and try to understand like what these values are about. Like not just about the definitions and formulas and so on, but why we need this and what we can understand about the data set with these metrics. So that's what we are going to see. So let's say that there are like 5 people, and we are going to analyze the salary or the amount of money a person is making. So let's say that we have like 5 people, from 5 different professions, and let's say that the first person makes $50,000, and the second person, let's say a doctor, makes $200,000, and then we have 150,000, 100,000, and so on. Let's say we have an executive or a businessman who is making like let's say 500,000 US dollars. So let's say that this is our data set. So now we have already discussed about this mean, right? So the mean of this particular data set where we have 5 people, so we add all their salaries and divided by the total number of values or the total number of people, which is 5 in this case. So you would add all these values and divide it by 5, and you would get 200,000. So this is the mean value. That means in this particular group, the average value, the mean value is 200,000. Okay. And now if we talk about this range is nothing but what is your smallest value and what is your maximum value. You find the difference, and that's your range. So this range tells you like how much different the lower value is and from the upper value. So in this case it's nothing but 500,000 minus 50,000. So if you take that, so if you subtract that, you would get like 450,000. So that is your range. So the difference between your lower value and upper value, that means like this is the difference between the two extremes, and that's what you call as range. And you can also represent range as 50,000 to 500,000. So that's the range that you give as like, you can say that in this particular data set we have people whose values range between $50,000 to $500,000. So you can also represent range in that way, where you give the lowest number and the highest number. When you subtract that, that's actually the actual value of range, which is 450K in this case, which is the difference between the lowest value and the upper value or the highest value that we have in a data set. And now we have the metrics such as variance and standard deviation, right? So let's talk about variance. Variance basically tells us how much each of these persons value differ from this average. So that's what we call as a variance. So you take each of this person's value, you subtract it with mean, and you again do some calculations and you get a single number. So if that number, that variance number is I, that means each of the person's salary is very different from the mean. So that's what we can understand. If the variance value is low, that means each of these persons value is closer to mean. But what I mean by saying like, or what I'm trying to say by telling that variance is closer to mean or variance is far from mean is, if the variance is far from mean, that means the data is like very spread. So it's kind of dispersed and the values are not closer to mean. And when the variance is low, that means like almost all the people make the same amount of salary which is closer to mean. So that's what we say. So when the variance is closer to mean, that means like all the people make the salary that is just around mean. If it's far, that means like it's kind of dispersed and so on. So that's how you can understand it in a simple way. So now let's try to understand about these metrics in individual way so that it makes like more sense, and we will also discuss about the formulas and how to calculate these. So let's see. So let's talk about this range, which we have already did, which is nothing but the difference between the maximum and the minimum values. So the formula is just pretty simple. So you just take the maximum number and divide the minimum number from that, and you would have this. So we have lower value and the higher value, and you would get the values like this. And what are all the applications of this range? So range is useful in scaling data. So in machine learning and deep learning, we do a process called as normalization, where we want all the values to be in the same range. So we would just like scale it such a way that all the values are between 0 and 1. This is because let's consider an example maybe. So we are working on a diabetes prediction use case, and one of the feature is age, and we know that age ranges from, let's say, let's say that the data set has age from 25 person with age 25, and the highest value in the age is, let's say, 75. So this is the range. So the values range between 25 and 75 in this case. And then now we have a blood sugar value, let's say that ranges from 80 to 150. And similarly, you have BMI that would range from 20 to 30 and something like that, right? So each of these features, each of these columns have values in different range. And when the values are in different range, it's kind of harder for some of the models, like a logistic regression model or a linear regression model, to work on the data set when the ranges are different. So we would normalize the data such that all the values lie between a specific range, let's say 0 to 1. So in those cases, this range metrics kind of helps us a lot in order to scale the data. That is like one simple example. And the other one is like range is helpful in detecting outliers or extreme cases in data. And again, these models kind of like the models that are non-tree based. So tree based models, for example, random forest and XGBoost, are not that much affected by the outliers. But when you have this logistic regression, linear regression, SVM, and so on, these models are affected by outliers, and range kind of helps us to identify these outliers, the ones that lie to the lowest value and the ones that lie to the extreme value. These kind of uh, tells us the outliers, and we try to process this outliers. Either you delete those outliers from your data set, or you would like replace those values with median and so on. So those are like few examples that we can work with. So this is the application of range, which is again, one is helpful in scaling the data, and the other one is like understanding the outliers in your data set. And the calculation is pretty simple, as we know. Let's say that we have four numbers, 3, 7, 2, and 9. So you take the maximum number, that is 9, and you subtract it with the lower number, which is 2, and you would get the range as 7. So this is how you can calculate the range. So now let's move to the next topic, that is variance. So variance measures the average of squared deviations from the mean. So again, this is all about the formulas definition, but in general, you can think about variance as, or understand variance in such a way that we are going to see how much different the values are from the mean. So that's all about it. So you have a data set of 10 numbers, and let's say that you have the mean as 5, and you see how much different or how these values, individual values, differ from the mean. So that's what variance is, and it's calculated by average of squared deviations from the mean. Let's try to understand this with the formula. And in formula as well, we have two different formulas. One is like population variance, and then we have populations sorry, samples variance. So this one is population variance, this one is like sample variance. So population variance is represented by this sigma square, and the sample variance is represented by s square. So this is squared because if your values is in the range of 5 to 10, your variance will always be in the unit of squared of those units. So variance is basically squared units, right? So that's why you kind of like representing it with square. And the formula is 1 divided by n, where it's kind of similar in both the cases. N is nothing but the total number of data sets in a population. But when you're working with the sample, you take this by n minus 1, right? So that's the difference. So when you're taking the population, so when I say population data and sample data, let's say that there are 1,000 people in a data set. If you're working with all these 1,000 data points, if you're trying to find the variance with all these 1,000 values, so then you divide that whatever we are getting over here. So we would divide that by n, which is the total number of values. But let's say that you're taking only 200 people or 200 data points as sample from the data set, you would subtract that by n minus 1, where n is again the total number of values in that particular sample. So that's what this n minus 1 is. Okay, so this is the thing, but the other half of this formula remains the same. So we have a sigma, which is the summation of xi minus x bar whole square. So this x bar is nothing but the mean of the data set, and xi is nothing but individual data set. So when you have like, let's say, 10 different values, you take each values, subtract it with mean. So let's say that one of the values is 5 and the mean is 10. So you say you take this 5 minus 10. So the difference is minus 5, and you would square that. So let's say that the other value is 3. So you would take this xi as 3. You subtract it with mean, which is 10. So it's 3 minus 10. So it's minus 7. You square that. So once you get all these difference of the value and the mean, so you square all those values and then you add it divided by n. In this case, you just divide it by n minus 1. So that's the main difference between them, and you would get your population variance or your sample variance. So that's how you would get it. And this is just like an example of how your data set would look like. So if you have a low variance, as I said in the previous slide, so low variance means the data points are spread around the mean, which is near mean. So that also mean that all the values are kind of similar, so they are not like dispersed in a larger range. So that's how you can understand about variance. So whenever you see variance is low, that means you can understand that all the values are around this mean, and we don't have a very dispersed data set like this case where the values are in kind of a larger range, which in this case it is kind of in a shorter range. So that's how you can uh, infer from a low variance data set and a high variance data set. So in this case, you see all the data points are within our kind of mean, and the other values are kind of spread out from the mean. So this is an example of high variance. So data points are spread near mean. In this case, that means it's low variance, and in this case the data points are spread far from mean, and then you have high variance. So individual circles here represents the data points, and this particular mark represents our mean. So this is about variance. So later we will also see how you can calculate the variance using this formulas with some sample data set. But before that, let's talk about the standard deviation. So standard deviation is the square root of variance. So it's very simple. Again, you have a population standard deviation and a sample standard deviation, and this is nothing but you just take a square root of variance. Either it can be a population variance or a sample variance, so you would get a standard deviation. And the main reason we have standard deviation is, as variance is a squared unit, right? So we won't be able to actually understand how this plays a role when you have, let's say, a data set. Let's talk about this first case. So you have 50k, 200k, 150k, and so on, right? So when you find the variance of this data set, your variance would be in the range of squared of these units, as variance is a squared unit. But when you want to understand the difference in the same range, you look at the standard deviation, because standard deviation is a square of variance. So let's say that the standard deviation is 70k, right? So that means like each of these values differ from the mean by 70k. So that's how we can understand that. let's come back to the standard deviation part. So standard deviation is the square root of variance, indicating the average distance of each data point from the mean in the same units as data. So again, standard deviation is just similar to variance as well, as we have mentioned here, saying that it indicates the average distance of each data point from the mean. So this is what we have talked about, right? The only difference is that it's same unit as the data, because variance is in squared units, but the advantage of standard deviation is that it's same unit as the data. Okay, so that's about it. It's pretty simple. It's just the square root of variance, and it's kind of in the same units as your original data set. And the formula is like, if you are working with population standard deviation, you just take the population's variance and you take a square root. If it's sample, you just take s square, which is your sample variance, take a square root, and that becomes your sample standard deviation. So when you have this I versus low standard deviation, this is how your data is going to look like. So when the standard deviation I, that means data points are more spread out, which can indicate more variability. And when the data points are closer to the mean, such as stability and less variability, this is when your standard deviation is less, just similar to the variance example. So this is how you can infer this. So I standard deviation means the data is spread out. That means each data point is different or far from the mean. And in the case of lower standard deviation, that means your data is like closer to mean. So that's how we can infer that. So let's try to understand this with some calculations. Let's say, let's take some sample data sets and try to put these formulas and try to calculate these values and understand this. So let's say that we have the values such as 12, 15, 18, 22, 27, 30, and 35. So here we have 7 values, and we are going to work on calculating the range, variance, and standard deviation. So range is simple, right? So we just take the maximum value and you subtract the minimum value. So here the maximum value is 35 and the lowest value is 12. So you subtract 35 from 12. So sorry, you subtract 12 from 35 and you get 23, right? So you have this 23 over here. And now let's use this population variance, because we are going to take this entire data set. So we have 1 divided by n, and you have summation of xi minus x bar, where xi is nothing but the individual data that we have over here, and x bar represents your mean or average value. So you find the difference, square it, and then you just like add it and then divide it by n. And the reason we have the reason we are squaring this difference is that the difference can be negative or positive. When you don't square this, the positive difference would cancel out the negative differences, but that shouldn't happen. So we have to take into account of both positive difference and negative difference. Positive difference and negative difference is nothing but this negative mean you have positive values. That's what I mean by that. So sometimes the difference can be positive or negative, right? So that would be cancelled out. So that's why we have to square it to take into account all the differences, irrespective of whether this number is smaller than the mean or not. So that's why we have that square. But let's not go too much into that. So this is the formula. Let's try to first calculate the differences. So yeah, I think so. Before, let's try to understand this mean, because we need this xi before we can find those differences. So mean is nothing but you just add all those values divided by the total number of values. So summation of data divided by the total number of values. So the total number of values is 7, and if you add the individual values, you would get 159. So 159 divided by 7 is approximately 22.71, right? So the next part, you calculate each deviation. So this xi minus x bar or mean is what we call as deviation. That's because this tells you how much each value is deviating from the mean, right? So that's why we call that as deviation. So calculate each deviation from the mean. That means subtract the mean from each data point, then square each result. Again, the squaring is just because that the negative errors and the positive errors shouldn't cancel out. So that's why we are doing that. So the first data point that we have is 12. So you take this 12 and put a minus, and you subtract your mean, that is 22.71 over here. So you, when you subtract 12 minus 22.71, so we are getting the value as minus 10.71. So you square that and you would get 114.68 and so on. So you take the second value, subtract it with mean, and then square it, and you have all those values, right? And now you have to do a summation, as we have this summation over here. And when you do this summation, you would get this 419.388 as your values. And here we are dividing it by the total number of values. If it's kind of sample if it's a sample variance, we would just put a -1 here, but this is for population, so you just like divide it by the total number of values. So you would have 419 divided by 7, and you would get the value as 59.91. So this is your variance. And if you look at it, it's not in the same range as this data, as variance is a squared unit. And if you want the standard deviation, just take a square root of this, so you would get the population standard deviation as 7.74. So Overall, our range is 23. So that means this is the difference between our lowest value and our highest value. And the variance is 59.91 and the standard deviation is 7.74. So what this standard deviation 7.74 is telling us is each data points differ from the mean by an average value of this 7.74. So this is like you can think about it as like each value is differing by this quantity 7.74 from the mean. It's kind of like taking the average of all those deviation, and that's how you can understand this. So in general, if the standard deviation is low, as we have discussed, all the values are closer to the mean. If the standard deviation is high, that means the data is dispersed over a long range and it's not kind of closer to the mean. So that's about it. So this is how you can calculate this range, variance, and standard deviation. So for range, you just multiply the lowest value from the highest value, you would get a range. For variance, it's 1 divided by n or n minus 1 depending upon population or your sample, and then just like calculates each deviation, which is x minus x bar, which is your mean, square it and then just add it and divide by n or n minus 1, and then standard deviation is just a simple square root of variance. So that's about the calculations. And when we talk about the importance of variance or standard deviation in the case of machine learning or deep learning, let's talk about this data quality check. So it also helps in to understand like how your data is spread and how it's affecting your model performance. So that's what we mean by this. So variance helps assess prediction consistency. High variance models may overfit while low variance model may underfit. So again, so it's kind of like you can remember this or you can try to understand like why we have this. So in general, we can say that if a model has high variance, that means it's overfitting. But when a model has low variance, that means the model is underfitting. So what we mean by this is, let's say that we have a model and you give different data points to that model. So first data set, it's kind of giving a prediction, and the second data set, we are changing a different test data and we are trying to predict over it. And in each case, we are trying to kind of calculate this variance. When the variance is more, that means your model's prediction is kind of like changing a lot depending upon the data. So that basically tells you your model has kind of memorized the data set, and that's what we call as overfitting, right? So overfitting simply means that your model performs well on training data, but it doesn't perform well on test data because it kind of overfitted to that training data. It's kind of memorize the data and it is not generalizing the data, so it won't be able to perform well on the test data. So when the variance is high, we can say that the model is overfit, but when the variance is very low, that means it's underfitting. So it's kind of like a rough fit. It's not like understanding the proper complex relationship between the data set, so it would tend to underfit. So it would perform well in some cases, but in most cases it wouldn't be able to capture the order relationship. So that's how we can understand this model's performance with the variance. And then you have normalization. So again, in normalization, we use the metrics, just standard deviation, variance, in order to kind of normalize this data. So even if you think about standardization, right, so we would uh, kind of try to put the values closer to the mean zero, and you would apply the standard deviation, you would standardize this data. So we do this thing. So this is another place where the measure of spread values are used. And then you have this gradient descent convergence. So convergence means it's where your parameters are optimum. So that means like when you use those parameters, your model performance is like good. So it's the loss value is less, it's performing well. But to reach this convergence, we kind of work with gradients to find like what's the optimum model values is going to be. So here we have this part where we say the variance of gradients affects learning rates. High variance can lead to unstable updates, while low variance promotes smoother convergence during training. So we know that we try to update these values, right? So we try to update the parameters. So you would have hyperparameters, and then you would have model parameters. In the case of gradient descent, the model parameters are updated at each step. So your model parameters would change. Let's say that we start with a model parameter of 10, and we either reduce from this 10 or we increase the parameter to 10, and we do this gradient descent thing. When you take this variance of gradients, when the variance is high in this case, that means the change is not stable. Sometimes it's kind of like moving around a lot. It's increasing and suddenly it's decreasing. So it's there is no stability there, and it's kind of hard for the model to reach the convergence. But when the variance is low, that means the change of the parameter values, if it's 10, it's kind of like changing in a regular pattern, and it's kind of the curve is smoother, and it would be able to uh, find the convergence in a better way. So that's like kind of the ways that where we inherently use these metrics such as variance, standard deviation, and so on, and that helps us to understand how this gradient descent and convergence happens well. So these are not about like explicitly using machine learning or deep learning use case, but all these tasks of your evaluation, normalization, and even this model optimization like gradient descent inherently uses these metrics such as your standard deviation, variance. The reason we are trying to understand about this is like once we understand this metrics, we would also be able to understand how these processes and happen, and that would helps us make better decision of, let's say, how you choose a learning rate, what's the scaling technique that we are going to use. So all this is going to be helpful for us. And apart from this, we also have a concept of bias variance trade-off, where we try to have a trade-off for a meeting ground between this bias and variance. So we don't want this bias to be high or low, and you don't have your variance to be high or low. So both these should be in a place where it's kind of helping the model, right? So it's kind of attaining a state where they can coexist in a normal value. So that helps us model perform better as well, as we have discussed here, right? So when the variance is more, you have overfitting, and the variance is low, you have underfit. So we need to identify an optimum value for this variance. So similarly, you have bias, which is nothing but the difference between your predicted value and the true value. So the model tries to add a error because we are trying to find the prediction for a real world problem. So there is of course a data error, right? So associated to it. So that's what we call as a bias. So this bias variance trade-off is something that we do in order to improve our model's performance, and also to solve this problem of overfitting and underfitting. In order to do this, you would have to do a trade-off between this bias and variance. So you have to try to see when we can kind of attain both good optimum bias value as well as over variance value, so that would give you a better model. So as I said, all these are used inherently in the different tasks that we do. Say for example, in the normalization, so all we do is just like go to Python, just use some functions to scale our data. We either use normalization, min-max scaler, or you use a standard scaler, and then we would just like use model.fit, and that would do this gradient descent in the backend, right? But understanding this math behind this, metrics behind this, helps us to understand what exactly happens there. And once you know what exactly happens there, will help us make better decision on what's the process that you're going to do in order to update your parameters, how you can optimize your parameters, and so on, and how you can even process your data. Say for example, normalization. So these are the things that are going to come in handy when we are good with the math part. So we will discuss about this gradient descent and bias variance trade-off and other things when we work on how to optimize our models, which we will eventually reach in our deep learning course. But for now, you can just understand this overview. So we have discussed about this range, variance, and standard deviation. So we have discussed about what these metrics are basically, and how to calculate these metrics using the formulas. And again, in a simple way, you can understand where are these metrics used. So later we will understand about each of these tasks in detail, so that it makes more sense. So that will be the agenda for today's video. In the upcoming video, let's just take these metrics, try to take some sample data sets in Python, and try to calculate these values, so that we get a hands-on experience of these statistical metrics. So I hope you have understood whatever we have covered today. So I'll see you in the next upload. Thanks for watching.